So next up is two population proportions. So we have the wine question, I believe, from the other flowchart. Following, maybe it wasn't, I don't know. But in a market research study conducted by Marilyn Merlot Winery on red wine preferences, the following results were found. Of a sample of 500 men, 210 preferred red wine, and a sample of 500 women, 120 preferred red wine. Conduct a confidence interval. Oh, construct. Yeah, I thought that was weird. To determine if the proportion of men preferring red wine is more than 15% higher than for women. Use a confidence level of 95%. All right, so is population proportion for men 15%? 15%? Yeah. Higher than for women. All right, type of interval. This would be a 2 prop Z interval. Reason being that, a little bit more elaborate than the last one, there are two proportions. That would be the men and women. Okay, so maybe it wasn't any more elaborate than the last one. All right. There are exactly two proportions, and that's it. Our assumptions. Looking for simple random sample of a sample. And a sample, no. Normal distribution not stated, but we can get after that by talking about the binomial cases. All right, so conditions. Binomial. Fixed number of trials. Yeah. Each one had a certain number of individuals sampled. Fixed probability. Well, whatever it is, it's fixed. Independent events. Well, just if one person likes red wine doesn't mean that no one else can. Or just because you're male doesn't mean that you necessarily have to like red wine, etc. And two outcomes. Yeah, you either like it or you don't. Or at least the way this is designed. So, therefore, normal distribution, because binomial distributions are a special case of normality. All right, NP greater than or equal to 5, and 1 minus P greater than or equal to 5. I might have written that down prematurely. Let's take a quick look. Well, yeah, it would have to be an assumption, even though it's a very reasonable assumption, since we were not given any indication of what the population proportion ought to be, or the difference in population proportion ought to be. I mean, a 15% difference could mean a lot of things, right? So it's a reasonable assumption that NP is going to be greater than or equal to 5, because with 500 people being sampled, it would have to be absurdly small in order to end up giving you something like 5, so yeah, 0.01 it looks like. So very, very small probability. So reasonable to assume that these values are going to be, in fact, greater than or equal to 5. Simple random sample. That wasn't stated, so we have to assume it. So 2 prop Z interval. All right, so then the big question would be, can we assume a pooled relationship? Can we assume that the two populations come from distributions that are roughly the same? Well, My guess is that there wouldn't be books written about, entitled Men Are From Mars and, or whatever it is. So I'm going to go ahead and say we can't make that assumption. Now, the question would be, can we assume a particular population proportion for either the men or the women? And again, that goes back to why we assumed NP and NQ are greater than or equal to 5, because we can't make that reasonable assumption. So our formula here appropriately should be P hat 1 minus P hat 2 plus or minus Z alpha over 2 times the square root of P hat 1, in the interest of space, Q hat 1 over N1 plus P hat 2 Q hat, poor quality hat, 2 over N2. All right, so let me get my information here. X for the men is going to be 210. So X1 is 210. Oop, get rid of that. N1, 500. X2, 120. N2, also 500. 95%, yep. So we can kind of cut to the chase on that and just say alpha is 0.05, which makes alpha over 2 0.025, which makes Z alpha over 2, because we've kind of beaten this to death a little bit, 1.96. All right. So then I just need 210 over 500. P hat 1 is going to be 0.42. P hat 2, 0.24. Just out of curiosity, the difference of about 0.18. Right, so it's in the neighborhood of 15%, so we'll see. All right, so is the difference between values going to be in the neighborhood of 0.15? Meaning, will our confidence interval contain 0.15? It's going to be a little easier to wrap this up once we get our interval than it was for the equivalent hypothesis test. All right, so it's kind of like with the hypothesis test, we had to do the confidence interval to follow it up. Here, we just have to do the confidence interval. All right, so P hat 1 minus P hat 2, we know is going to be 0.18 plus or minus 1.96 times the square root of 0.42 times 0.58 over 500 plus 0.24 times 0.76 also over 5 of the hundo. All right, so just computation time. Inverse norm. Just want the more exact. So our margin of error value, so we're looking at 18.18 plus or minus roughly 0.0572. So the difference in P, so P hat or P1 minus P2 is going to be living in between, on the low end 0.122, well 123, sorry. And then on the high end 0.237. All right. So that gives us everything we need, because we are 95% confident that the difference in population proportion of red wine preference will lie between 0.123 and 0.237. All right, so this would be consistent because the null hypothesis, we're talking about the difference being equal to 0.15. All right, so it's weird, but we would say the HO would be, it still has to have equality. P1 minus P2 is equal to 0.15. Doesn't have to be equal to 0. All right, so it just usually is equal to 0. And so, we took a different approach when we dealt with the hypothesis test. But if we worked with this as our null hypothesis, it would have kind of streamlined things, but it also would have required us to learn a different type of hypothesis test. So I figured I'd use the combo approach. All right, so here's 0.1, 0.15, 0.2, 0.25, spacing notwithstanding. 0.123 is like right here. 0.237 is like right about there. And so 0.15 does fall in that interval, that 95% confidence interval. So construct a confidence interval to determine if a proportion of it is 15% higher than that of women. So proportion of men is 15% higher than women at the point, or well, really 0.05 level, at the 95% confidence level. And because we use the p-hat version of the formula, this is also something that you could have chucked into your calculator and gotten the values for. And there it is. Last but not least is two population means, the independent samples case. All right, so same information from the equivalent hypothesis test. Again, we're just looking at it in the case of confidence intervals, or at least from the standpoint of confidence intervals. So we want to know if there's a significant difference in the number of pedestrians. So all right, so the type of interval is going to be a two-sample t-test. And that's because we have two means with independent samples. When you're dealing with assumptions and conditions, you can kind of rely on the familiarity that comes from testing claims about population means, whether it's one or two samples, because it's always going to have the same framework. Slight differences here or there, but we need to know whether or not there's simple random samples. Let's take a look. Random sample, okay. Nothing about normality, I don't believe, but the size, number of hours sampled, is greater than 30. All right, so our conditions here we have simple random sample. I'll just use ND because N1 and N2 greater than 30. Sigma is unknown. All right, so calculator functions to sample t interval. All right, the only question that comes into play is whether or not we should be using a pooled approach. The pooled approach, again, only occurs when you're dealing with samples that we know have come from the same population. There's no guarantee for that. So we're going with the unpooled approach, x bar 1 minus x bar 2, plus or minus T alpha over 2 times square root of S1 over N1. S1 squared over N1 squared, N1 plus S2 squared over N2. So X bar 1, we're just going to jot it all down on the side as per usual. 421, S1, $1.22, N1, 35, X bar 2, 347, S2, 85, N2, 50. We need our T alpha over 2. So inverse T, this is 0.025 with degrees of freedom is going to be 34. So in this case, it's going to be N1 minus 1. So 34. We choose the smaller of the two. All right. So let me get that. So negative 2 point, well, so plus or minus 2.0322. All right, so we got all those values to chuck in here. I can do the 421 minus 347 on the fly here, so 74. Plus or minus, again, 2.0322. $1.22 squared over 35 plus 85 squared over 50. All right, so number crunching time. It's clobbering time. Movie reference. First one to send it to me gets a bonus point. So unless I miscalculated, which is entirely possible, we are looking at 25.491. This would be the difference in the means, population means, so mu1 minus mu2. And 122.509. Now you can check it on the calculator, and if you do, you get something in the neighborhood. You get like 26.193, 121.81, and that's because the calculator uses a different method for coming up with degrees of freedom. So, you know, it's a little give and take kind of approach. If you want to get the values that the calculator has, then one thing you could do is go through the approach for finding a 2-sample t interval on the calculator first, get the calculator's degree of freedom, and then use that to determine your inverse t. I think that's probably unnecessary. The better way of handling it is to just do it the way I showed you and know that there's going to be a slight discrepancy in the way the calculator computes it and the way you get it. All right, both are correct and both are acceptable by the AP. It's just you don't really have a method to justify where you would come up with that degrees of freedom that the calculator says is 56.504. All right, so the by hand way is unfortunately or fortunately, depending on how you like to do things, better in this regard. So we are 95% confident that the difference in population mean number of pedestrians is between 25.491 and 122.509. this measure is inconsistent with the null hypothesis of an equivalent hypothesis test, because that null HO would be that mu1 is equal to mu2, which is the same as saying mu1 minus mu2 is equal to 0. All right, so 0 does not fall in this interval. All right, so I could put it on a number line, but here's 0. Let's go with it's going to look kind of absurd. That's really what I'm getting at, because it's nowhere near capturing the 0. The scale makes it look like it might be, but in the grand scheme of things, it's not even remotely in the neighborhood. All right, so just to answer their question, is there a significant difference? All right, there is a significant difference. So the purpose behind all of these videos was twofold. One was to give you a nice review, hopefully, of the different types of confidence intervals that you could employ. But the other is to show you how you can draw the same types of conclusions using a confidence interval as you could with a hypothesis test. All right. So, at a minimum, you now have a quick and easy way to come up with the results of a significance test without having to construct the full-blown significance test. And there it is.